Okay, so let's start. All right, so what we have to show or prove is that for a complex number z, that's what z and c means, that the quotient z plus 1 over z minus 1 to the 5th power equaling 1 has solutions of the form z equals I times cotangent of n pi over 5. How do we do this? Well, it turns out that at the heart of solving this is Moivre's theorem for kth roots of a complex number. So if we have a complex number, let's say a, we know that a can be written as r cis theta, right? It's technically r cis theta plus 2 n pi, where n is in z, right? It's just that theta is the principal argument, so n is in z, n is an integer, right? Okay, but we know that a complex number a can be written in this form. Got it. And we know from Moivre's theorem, so far I have a video on Moivre's theorem for raising a complex number to the n power, but I don't have Moivre's theorem for kth roots of a complex number, so I'll make a video on that. But it turns out that if you want the kth roots of a, that is if you want a to the 1 over k, then what you have to do is do r to the 1 over k, and then I'll write it, but let me do the blue stuff first. Cause I'm blue, okay, alright. And so 1 over k here, and then it's gonna be over k here. I should have closed the n blue. Okay, over k, where n ranges from 0, 1 to all the way to k minus 1. Now, again, I'll dedicate a video to this and explaining it thoroughly and saying why it works the way it does. But notice that we're saying for a complex number a that it has a total of kth roots. So in other words, the 5th roots of a complex number are actually 5 numbers. Now, I will say more on that when we get to it, but as I said, we need to use this here. Okay, to start, let's make w the quotient z plus 1 over z minus 1. Now remember, z itself is a complex number, and obviously as w is a quotient of two complex numbers, z plus 1 and z minus 1, w also is a complex number, right? Okay, now notice that what we're going to do is solve for z. What we need to do is solve for z. But since now we have our equation turning into w to the 5th is equal to 1, let's first solve for w. Well, solving for w amounts to raising both sides of this to the 1/5 power. So w is equal to 1 to the 1/5. I see. So w is the 5th root of unity. So 1 to 1 over k we call kth root of unity, right? And so I'll dedicate a different video to talking about the kth roots of unity, right? So the kth roots of unity. But for now, in this video, hopefully you have enough familiarity with roots of unity so that you can understand this video. All right. So 1. Remember, the 5th root of 1 so far in your knowledge is just 1. So there's only 1 5th root of 1, but that's not true. There are 5 5th roots of 1. And it's just that the other 4 are complex. Of course, 1 is the 5th root of 1, but it's only 1 of 5. Okay, so what are the others? Well, we'd find them here. Let's first write 1 as a complex number. 1 is equal to 1, r is 1, and then it's going to be cis, and then theta is 0, and then plus 2 n pi, again n and z. So that's 1. What I'm saying is that the number 1 is equal to, right? I'm saying the number 1 is equal to 1 cosine 0 plus I times sine 0. And that's in fact true because sine of 0 is 0, so cosine of 0 is 1, so 1 equals 1 is what this says. Yes, I have the 2 n pi because remember, like, we can use coterminal angles as the angles of the complex number, so we could keep adding multiples of 2 pi or keep subtracting multiples of 2 pi. That's why the 2 n pi is necessary there. But the principal argument of the complex number 1 is 0. Principal argument is referring to theta. And that's just the angle between 0 and 2 pi. Because as I said, you can keep rotating, coming back to the same angle, right? Okay. So we're saying for 1, theta is equal to 0, right? Okay, all right. If that's the case, then it looks like the fifth roots of 1 should be 1 to the 1/5, right? They should be equal to, well, 1 to the 1/5, that's the r to the power 1 over k. And then otherwise, cis 0 plus, and then it's going to be 2 pi n, right, over k, where k n goes, right, n goes to 0, 1, 2, and I should have written here k is 5, so let's replace this k with a 5. 1, 2, and then all the way to k minus 1, so that's going to be to 5. And there's not that many to write, so I'll write them all. It doesn't go to 4, sorry, it goes to k minus 1, so it's 5 minus 1, therefore 4 there. Okay, so there are 5 fifth roots of 1, and roots of 1 are called roots of unity. So I'm saying there are 5 fifth roots of unity, and this expression, notice, can be simplified to just, we don't need to write 0 plus, we could just write 2n pi, right? Okay, so it's that. And obviously 1 to the 1/5 is just 1, so I could get rid of that. So if we replace n with 0, we get cis 0, that's cosine of 0, plus I times sine of 0, that's 1. So one of the fifth roots of 1 is 1 itself. But if you want another one, cis, and then if we replace n with 1, it'd be cis 2 pi over 5. Basically, they are this, like the fifth roots of unity are like on the real imaginary axis. Like one of them is 1 itself, it's right there. The others, well, what's 360, which is 2 pi divided by 5? It's like a lot. I'm not good at like basic arithmetic. What's that, y'all? Like, I don't know. It's not like you can help me. Lonely. No, just kidding. Okay, so 7, and then 7 times 5 is 35. My bad, y'all, that I'm making you watch this. And then that's 272. Okay, so what we do to find another one is we go to a 72-degree angle from the x-axis. So let's say that that's here. So this is the other. And of course, I'm saying the radius of the circle is 1 because they're roots of unity. And then another 72, which would put us at 144, would give us the other one. This one corresponds to cis, and that's when n is 2. Cis, that's 4 pi over 5. So this one right here is cis 4 pi over 5. Right? Okay, I'm already doing more than I should on nth roots of unity, but there's 5 of them, as I said, spread 72 degrees apart. And what's that? 1, 2, 3, 4, and so the fifth one is going to be right here. Yeah, all 5 of them are captured in here. Yeah, and that's again when n goes to 0, 1, 2, 3, all the way to 4. Fine. How is this helpful? Well, because now what we know is, notice that like we're saying w is the fifth roots of unity, so this here is w. This expression right here is w. So I could get rid of this and be like, this is equal to w, the 5 fifth roots of unity, with this prescription also like together, right? Okay. And I don't need this, but I need, the space. Okay. So, and we don't need this anymore, right? Yeah, again, I will dedicate a video on how to use de Moivre's theorem for kth roots. Okay. But now, since w is equal to this, and we also know that w is equal to z plus 1 over z minus 1, what we have is z plus 1. Remember, we're trying to show that z has to look like this. Let's not lose sight of where we're going. Z plus 1 over z minus 1, we're saying it's equal to, this is equal to, it's equal to w, the 5 fifth roots of unity. And so that's cis, and then 2, and then n pi over 5, right? Okay, cool. And just put down in your head the n varying from 0 to 4. Otherwise, I won't write it because it'd be too much writing. Now, for what I'm about to do next, let's call this x, right? Yes, we know it's w. but let's call it x, because now we need to solve, and so x is a complex number. I'm renaming w. Okay, so then our equation here, remember, because we need to solve for z, is going to say this. I'm just trying to get to z efficiently without having to rewrite this over and over. So I have that. So if we multiply both sides by z minus 1, we're going to get z plus 1 is equal to x times z minus 1. Right? Okay, and we'll plug back what we said was x, which is this. Okay, and so then now the next step in the algebra is to write z plus 1 is equal to xz minus x. Cool. And then we want to put the z's together since we're trying to solve for z. So that's going to say z minus xz is equal to minus x and then minus 1, right? Okay, cool. And so then we're going to factor a z and be like z times 1 minus x is equal to minus x minus z, minus x minus 1, right? Okay, cool. And so then we see that z is equal to, where should I write? I guess I could write over here. So we're going to see that z is equal to, it's equal to x minus x minus 1, which is minus x plus 1, right? So this, right there, divided by 1 minus x. Okay, 1 minus x. Now, if I give this negative sign to the denominator, we can write it a little cleaned up as x plus 1 over x minus 1. In other words, this minus got swallowed by this to turn into that. So this turned into this after I put a minus sign in the denominator. Take this and put it there. Okay, 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 good. So now we've got what z is. Good. And we could erase this, make space. Okay, so z is equal to, it's equal to x plus 1 over x minus 1. So that's going to be cis 2n pi over 5 minus 1 divided by cis 2n pi over 5. Oh, this is plus 1, my bad. Plus 1 minus 1. Okay, all right, hope you had faith. Okay, all right. So where to from here? Well, we need to somehow turn this z into this. That's what we have left to do, okay? All right, give me 1 sec. Okay, so like Einstein said that you should never like memorize something you could just look up, but obviously like by doing something over and over, you like forcibly committed to memory at the end of repetition. So that's good, but he's right? Like don't memorize anything you could look up. So I haven't used these guys enough to have committed them to memory. These are what are called the product to sum formulas in trig. So I'm guessing that we might need these at some point. There's nothing else written on here, okay? So I'm not cheating. Okay. All right, but we're gonna need them at some point is what I'm saying. Okay, cool. Because what could we do next? Not much. So what we could do is, I suppose, expand what cis is, right? And multiply by conjugates, because that's always a good idea, right? So we go, cis is cosine, and so the numerator is cosine 2n pi over 5, and then plus I times sine 2n pi over 5. Notice that what I write over here, that's going to make the imaginary part of the whole numerator, but 1 is a real number, so maybe we should put the 1 that was here together with the real part. So this is from the cis. We're not done interpreting the cis, but this is the real part of the cis, and so plus 1, and then we have plus and then I times sine of 2n pi over 5, right? Okay, cool. So we have that, and then of course the denominator is going to be it's going to be cis, so cosine 2n pi 2n pi over 5, and then minus 1, and then plus I times sine 2n pi over 5, right? Okay, as you can see, if I'm going to multiply this quotient by the conjugate of the denominator, and that's usually what we want to do, right? Multiply by the conjugate of the denominator when we're doing a quotient of two complex numbers. But if I'm going to do that, I'm going to have to write this 2n pi over 5 over and over and over. So I'm going to define 2n pi over 5 to be some angle alpha. That way I don't have to write it in this form, I could just claim it to be alpha. So what I'm saying is the denominator now is, this is alpha. Well, everywhere we see this, it's alpha, right? Okay, so alpha. Okay, cool. And also notice that this is the real part of the numerator and this is the real part of the denominator. Okay, so what we're going to multiply by is by the conjugate of the denominator, which means we turn that plus sign into a minus, right? So check this out. So z is going to then be equal to we have in the numerator we have cos alpha, and I'm gonna discard the parentheses around cosine and sine, that way I don't have to write so many parentheses. Cosine alpha plus 1 and then minus I times sine alpha, right? I don't need a parenthesis there. Okay, my bad, guys. Okay, and then the denominator is cos alpha minus 1, and this is a plus right here. Okay, and then plus I times sine alpha, right? Okay. All right, and the conjugate of the denominator, remember, is going to be like, this does not look a cos alpha, my bad, guys. The conjugate of the denominator is going to be, as I said already, changing this into a minus, changing the sign in the middle, right? Okay. But why is it that when I had a minus 1 right there, the minus 1 is with the 1, it's not in here, so that is deservedly a plus, so I go minus 1 right here. Sorry, I was just rewriting there in case you were confused. I was just making sure that we didn't make like a careless mistake and wrote a plus there when it should have been a minus. It's a plus, as should be, but yeah, because obviously like we would have done a lot of work to no avail otherwise. Okay, so all right, now multiplying by the conjugate of the denominator, as I said, we're going to have to do cosine alpha minus 1 and then minus, right? I'm changing that sign right there, minus I times sine of alpha, right? Okay, cool. And then we're going to multiply by this in the numerator also. So this is cos alpha minus 1, yeah. And so that's going to be cos alpha minus 1 and then minus I sine alpha, right? Okay, all right, and I need another parenthesis here, and I suppose I needed to keep the parenthesis that was there. Okay, cool. All right, are there any conveniences? Because man, this is getting ugly. Like yeah, there are conveniences, because, well, we can see that in the numerator we really have something ugly. So there aren't too many conveniences just yet in the numerator. Notice that we are going to FOIL. First we multiply these two, then these two, then these two, then these two. I hope like this somehow works out. And it will. Okay, so it's well planned. So z is going to equal, well, cosine alpha plus 1 times cosine alpha minus 1, notice, is a difference of squares. It's of the form a minus b times a plus b, so that's a squared minus b squared, where a is cos alpha and b is 1. A is cos alpha, b is 1. A plus b times a minus b, that's the first product, right? As I said, that's a squared minus b squared, so it's going to be cos squared alpha and then minus 1 squared, or just simply minus 1. Okay, we are done with the first arrow. Next, we multiply this fella and this fella, right? And what we do, we're going to get minus I times sine alpha, cosine alpha, and then what is it going to be? Minus I times sine alpha, cosine alpha, and then minus I sine alpha, right? Minus I sine alpha. Okay. All right, just because we're going to run out of space, the next two arrows, which is this times this and then this times this, I'm going to write below this, right? Okay, so when we multiply this and this, what we're going to get is plus I times sine alpha cos alpha. So I'll write that right here, plus I times sine alpha cos alpha, right? And then when we multiply this and that, we're going to get I squared, and then it's going to be, whoa, we're not done distributing this. Sorry, my bad. We're not done with this arrow, this little guy. We did this times this, but we need to do this times that. So we still have a minus I sine alpha to write. Minus I sine alpha. Got it. But then now, as I had won it, we go to the last arrow. The last arrow is multiply this fella and this fella. Ah, how nice, because that's going to be a negative I squared. But I squared is negative 1, so negative I squared is going to be plus. So we have plus, and then it's going to be sine squared alpha otherwise, right? Plus sine squared alpha. Ah, how convenient, because look here. This is all like in one line. It's supposed to be in one line. So we could add these two together, and we know from that really important identity in trig that sine squared plus cosine squared is 1. So this is 1. So we have 1 minus 1 because of that minus 1. So this whole thing disappears. It becomes 0. So this becomes 0. Got it. And right here, right, like these two guys are the same but opposite in sign, so they turn to 0. So the whole numerator of z just simplifies to minus 2i sine alpha. Got it. Beautiful. How nice. Minus 2i sine alpha. Got it. All right. So what about the denominator? Because we still have to do the denominator, don't we? And in the denominator, the first arrow in the foiling is going to be like multiply these two, right? And then the next arrow is multiply these two, then these two, then these two. But if you look, big picture, there's a difference of squared situation, because cosine alpha minus 1 is the same as this here. So let's say that that's a. So this is a. And then we have I sine alpha and I sine alpha here. So let's say I sine alpha is b. So we have a plus b times a minus b. We said, using difference of squares, that that's a squared plus b squared. Okay, where again, a is this and b is this. B is with the I, right? So a squared plus b squared is going to be cosine alpha minus 1 squared. And then plus I times sine alpha squared. A squared plus b squared. Got it. But then let's just work on the denominator. Cosine alpha minus 1 is going to be cosine squared alpha minus 2 cosine alpha, and then it's going to be plus 1, right? Okay, and so this here is just this, and then we have plus, and then I squared is negative 1, so minus, actually minus, and then it's going to be sine squared alpha, right? Okay, cool. So where to from here? Je ne sais pas. But wait. Did we have a minus sign? Yeah, it's not going to be a squared plus b squared. It's going to be a squared minus b squared. Well, it's going to be a minus. This was a plus, sorry. Yes, this is, my bad, guys. My bad. We said that this was a and this is b, so a plus b times a minus b is going to be a squared minus b squared. So what I should have written is a squared minus b squared. I knew there was something problematic here. So this here, right, this here is this. Okay, and then we would have had a blue minus sign here, and then I sine squared alpha is going to be, well, I squared, which is negative 1, that's that negative, and then otherwise sine squared. But we'd have minus minus, first minus being that blue minus, so this is actually a plus right here, and it needed to be, because otherwise there were no conveniences in the denominator. Okay, but now there are, because now we have cosine alpha plus sine alpha, that's 1, but with this other one they make 2, so we have 2 minus 2 cosine alpha. That's the denominator. Okay, so the denominator is 2 yes, 2 minus 2 cosine alpha. Alright, man, is this gonna ever get there? Like, cause look at what we have to do and look at where we are. Like, it's a mess. Yes, but it's gonna work out. Okay, I'm speaking about math. Not anything else. Okay. All right, so where do we go from here? How about we factor out a 2 from the denominator? I know that's not much. So what that means is, like, we put a 2 right here and then parenthesis a 1 right there, right? All I did is factor out a 2 from the denominator. It'll make it a little bit easier to look at, so I cancel those 2. So right now we are saying that z is equal to, minus I, and then sine alpha over, and then it's 1 minus cosine alpha. Remember what we said is alpha because we got to somehow get back there. Okay, so where to from here? Well, I think what we should do is, for lack of better ideas, we should multiply by 1 plus cosine alpha top and bottom. So that's what I'm going to do. So I'm going to multiply top and bottom by 1 plus cosine alpha. Got it. So 1 plus cosine alpha. Okay, so when we do, the denominator is going to turn into 1 minus cosine squared alpha, right? Okay, 1 minus cosine squared alpha is, remember from that Pythagorean identity of trig, which is really important, sine squared plus cosine squared equals 1, so 1 minus cosine squared is sine squared. So we go, all right, this is just sine squared alpha, which is sine alpha times sine alpha, if it's easier on the eye for you when I write it that way. Now look here, so what we're going to do is we cancel here and here. So we're going to get minus I times, and then it's going to be 1 plus cosine alpha over sine alpha. Okay, so this is equal to z right now. And this somehow needs to turn into I cotangent n pi over 5. Okay, perhaps it is here where we should recall what alpha was. It's 2n pi over 5. So right now we have z is equal to minus I times 1 plus cosine. I'm going to replace alpha with what we know it is. It's 2 times n pi over 5. Now notice that this 2n pi over 5, which is our alpha there and there, is not the same as this. This does not have a 2. It's n pi over 5, right? Okay, so maybe we can use a cosine double angle identity in this part is what I'm saying. Okay, cool. And then we'll have over, and then sine of 2 n pi over 5, right? Now, I guess I don't need any of this anymore, other than remembering alpha was 2n pi over 5, but we just used it, so we don't need it now, Mel. All right. So we go, all right. So remember that cosine 2 beta, from the cosine double angle identity, has 3 versions. One of them, perhaps the most popular, is 2 cosine squared beta minus 1. And as I said, there are 3 versions, but we're going to use this version here because, well, I like the convenience that we have a positive one. When I replace this with like 2 cosine squared n pi over 5 minus 1, the minus 1 and the plus 1 here will take care of each other. Yeah? Okay, cool. So that's what I'm going to do. So z is equal to minus I times, and then 1 plus, and then cosine of 2 beta, so I'm saying beta is n pi over 5. Cosine of 2 beta is going to be 2 cosine squared of n pi over 5, and then minus 1, right? Okay, cool. So this is the entire numerator, okay, over, and then the sine 2 beta formula, there's only one, we're pigeonholed into it. Sine 2 beta is equal to 2 sine beta cosine beta, right? All right, cool. So, as we expected, we're going to be able to cancel this and that. And so then we're going to get, well, let me write the denominator. 2 sine beta cosine beta is what we have right there, right? Okay, cool. And that's just a translation of this. I'll replace the beta with n pi over 5 soon. So we'll have z is equal to minus I times, and then there's a 2 there, so minus 2i, and then it's cosine squared, so it's cosine n pi over 5 times cosine n pi over 5. Okay? And then over, and then in the denominator it's 2, and then sine n pi over 5 times cosine n pi over 5, right? Okay, so we cancel the cosine n pi over 5 right here and right here. We cancel the 2's, and we're gonna get that z is equal to minus I times cosine n pi over 5 divided by sine n pi over 5. Okay, Okay, all right, and of course, sine over cosine is cotangent, so there had to have been a negative sign right here. Otherwise, like, this problem is wrong, because our conclusion says now minus I and then cot and pi over 5. But when I wrote it, there wasn't a minus sign right there. All right, hold on 1 second. Well, maybe not 1 second, like more like 15 seconds, okay? All right. Like a rapper, I have 2 phones. Like, hold on. Like, a student sent me this question. It's not in this one. Okay. Or maybe I just lied. Like, just picked up the same phone. All right, so. Wait, where the heck is this question? This daggone question. Come on. Wait, kid, you sent me that question, did you not? What? Okay, well, yeah, I can't seem to find it. I thought I had a picture of it. It was like the last question on the list of like challenging questions, but I can't find it. Like, see, I'm not lying. Okay, thank you, Jesus. Okay. Well, alright, whatever, I can't find it. So, there has to be, like, a minus sign right there. Because, like, yeah, like, this guy, like, took his dogs inside of a bank. And so a manager at the bank was like, hey, can't you see the sign there? It says there are no dogs. And the guy goes, well, the sign should say there are 2 dogs. The sign is wrong. So that minus sign is wrong. Keep watching. Take care.